Hey guys, today we're doing Chapter 10, Section 7, which is on sampling distributions and the central limit theorem. Before we actually start the lesson, I'd like to just go through this activity real quick. Basically what we're going to be doing, we're going to be doing some random sampling and getting some data, and then we're going to be applying the central limit theorem to see how it works. So the first thing they ask is to find the mean and the standard deviation of the numbers from 0 to 9. If you are not sure how to do that, you can always go to Stat Edit on your calculator, and in your list 1, just enter the numbers 0 through 9. And then you can go to your one variable stats. If you go to Stat and then Calc and 1 var stats, it'll give you all of the information for that data set, which was 0 through 9, including the mean and the standard deviation. And you should find that the mean is 4.5 and the standard deviation is 2.872. Okay? Now we're going to do a little simulation to come up with some values here. And we're going to choose a random sample of 4 from the numbers 0 through 9. We're going to run the simulation and calculate the mean of the 4 numbers that occur, and we're going to repeat 24 times. So what I'm going to do, I've actually already done the simulation. I'm just going to fill this stuff in. And what I did to get my 4 numbers was rand_int 0, 9 on my calculator. So it gives me a random integer between 0 and 9. And then I just hit enter 4 times for each of those trials. So for my first one, I got 4, 7, 0, 3. Those are my 4 numbers. And then I just went through real quick and calculated the mean to get 3.5. So let me fill in my chart, and then we'll look at our data. Alright, so I've got all my data entered into my chart from my experiment. Here are all my 4 random numbers, and then here are all my means for those numbers. So then when I get down to the bottom here, it says draw a histogram to illustrate the distribution of your sample means. So we had 25 trials here for this experiment, and basically what I'm looking for is I'm trying to find how many times each one of these occurred. So really, I had 4 numbers for each of the trials, therefore this is going to be out of 100. So for my zeros, I'm going to count up how many zeros I had, put them out of 100, and then that's going to be my relative frequency. Okay, so when I do my relative frequency chart, it's going to turn out to look something like this. So you can kind of notice that it looks kind of like a normal distribution, or a standard normal distribution, because it's got that bell curve going on, where these are my relative frequencies. Okay. So now what I want to do is I want to calculate the mean and the standard deviation of my sample means. So what that means is I'm going to calculate the mean and standard deviation of this data set here. So again, what I'm going to do is go on my calculator, going to enter my means into my list 1, and then I'm going to do my one variable statistics for that set. And for me, when I calculated it, for my mean of my sample means, I got 4.54, and for my standard deviation of my sample means, I got 1.5. Now, how does that relate to my original data here? Well, you can see that my original mean was 4.5 and my original standard deviation was 2.8. So, my mean is close, my standard deviation is a little bit off. Okay? But basically, this leads us to the central limit theorem, which we're going to talk about up next in the notes. Alright, so now we're going to do Chapter 10, Section 7. And you'll notice that the first thing we have up here are some vocabulary / symbols that we need to know. So X bar, that's your sample mean. So that's the mean that you get from the sample, or the sample that you actually experimented with. Mu, that's your population mean. So that's the overall mean if I'm looking at the entire population. And then mu minus, or mu sub X bar, okay, that's the mean of a set of sample means. So what we actually found in that activity, that very last thing that we found, instead of calling it X bar like I did, what you should have done is called that mu X bar, mu sub X bar, because that's the mean of your sample means. Okay, we also have S, that's your sample standard deviation. So that's the standard deviation from a specific sample. We've got sigma, which is your population standard deviation, so your overall standard deviation. And then we've got sigma X bar, so sigma sub X bar. That's your standard deviation of a set of sample means. So that, again, was that last thing that we calculated on the activity. That was, according to your sample means, what was our standard deviation. So this leads us to the central limit theorem, which is on page 673 of your book. The central limit theorem says, suppose random samples of size n are selected from a population with mean mu and standard deviation sigma. Then, as n increases, the following occur. The mean, mu sub x bar, of the distribution of sample means approaches mu. So we saw that in our activity. We saw that our mean, our original mean, and the mean of our sample distribution were very similar, okay, as I was doing more trials. Number 2, the standard deviation, sigma x bar, of the distribution of sample means approaches sigma over the square root of n. So looking at our in-class activity that we did, for each of our different trials, we had 4 possible numbers that we were looking at. So we were finding the mean of 4 numbers, essentially. So my sigma was 2.872. My n value was 4. So if I take 2.872 divided by the square root of 4, it's 2.872 divided by 2, which gives me approximately 1.44, which, if you notice from the activity we did, that is approximately my sigma x bar that I got. So it works out. And then number 3, the distribution of sample means approaches a normal distribution with a mean of mu and a standard deviation of sigma divided by the square root of n. So that's our central limit theorem. Let's do some problems. In a certain country, the distributions of heights of young adult males can be modeled by a normal distribution with mu equals 66.5 and sigma equals 2.7. A medical study is conducted in which men are randomly selected from this population in sample sizes of 225. The mean height of the men in each sample is recorded. We want to estimate the mean and standard deviation of the numbers recorded. So in order to do that, we're going to use our central limit theorem. And I know that mu x bar is going to be approaching mu, which was just 66.5 inches. So that's what I would estimate for the mean of my sample set. Then for sigma x bar, well, that's going to be sigma over the square root of n. So that would be 2.7 over the square root of 225, which gives me approximately 0.18. So my mean is going to approach 66.5. My sigma is going to approach 0.18. Then it says, describe the distribution of sample means. Well, I can say the distribution of sample means will approach a normal distribution with a mean of 66.5 inches and a standard deviation of 0.18 inches. Okay, then it says the CLT is central because it deals with the mean of a population, which is a measure of center. It is a limit because it deals with what can be expected as samples of larger and larger sizes are involved. So basically we're combining this idea of measures of center with limits to create this central limit theorem that tells us as we approach a larger and larger number of trials, what's going to happen to our measures of center and our measures of spread. So a corollary to the central limit theorem says that the central limit theorem will always hold if the population itself is normally distributed or if the sample size is greater than or equal to 30. So as long as one of these two things occurs, we know that the central limit theorem will hold. So let's look at this last problem here. Suppose a car manufacturer claimed its new economy car has an average highway gas mileage of 37 miles per gallon with a standard deviation of 5 miles per gallon. After receiving numerous complaints, a consumer group decided to test a random sample of 40 such vehicles. For the sample, they found the mean gas mileage to be 35 miles per gallon. At the 0.01 significance level, test whether the average gas mileage is less than the manufacturer claims. Be sure to state your hypotheses clearly. So first thing we need to do is look at our null and our alternate hypothesis. So my null hypothesis is going to be that the average is 37 miles per gallon, because that's what we want to assume is going to be true, which means that our alternate is that it's not 37 miles per gallon. Okay, so that's what we're trying to test. So I know from my data here that my x bar is 35. Okay, I also know that my mean is 37. I know that my sigma is 5. So if I want to find my sigma over square root of n, which is my sigma x bar, that's going to be 0.791. Because sigma is 5, my n is 40, because I tested 40 cars. Okay. And I'm trying to test this at the 0.01 significance level. So I've got all my values here. I'm testing this at the 0.01 significance level. And I need to think about what is less likely to happen than what actually happened. So what actually happened was I found the mean to be 37. I know that it should have, I found it to be 35, and I know that it should have been 37. So what I'm going to do is test everything less than 37. So I've got the probability that x is less than 37. Okay, to calculate that, I can find my z-score. So I'm going to standardize my data set. So I take, for z, I take my x bar minus my mu divided by my sigma x bar. So that's 35 minus 37 over 0.791, which gives me 2.53. So this is actually going to be the probability that z is less than negative 2.53. Okay, so then if I look at my chart, okay, I'm going to calculate that probability using my charts, and I find that that's 0.0057. So 0.0057 is less than 0.01, my significance level. So what that means is that I have to reject my null hypothesis and accept my alternate. All right. And that is everything for section 7.